Hello everyone and welcome to this video on voltage level shifters. In this video we're first going to briefly discuss what voltage level shifters, or actually sometimes they're called voltage translators, what these are and when you use them, and then we're going to look at different kinds of implementations of level shifters. In particular, we're going to look at a solution, a single transistor solution that you could buy from Sparkfun electronics, and we're going to measure its performance and discuss the difference between an open drain and a push-pull output configuration. So what are level shifters? Imagine that you have a 3.3 volt system over here and a 5 volt system over here. This could be a Raspberry Pi and this could be some sort of Arduino. And you want to connect the two, let's say over a serial link. Now if you just connect the two, you run into two problems essentially. Let's assume that the 3.3 volt system is transmitting a logic 1. So some transmit line is going to sit at 3.3 volts. And the 5 volt system really expects a 5 volt or something around 5 volts to trigger a logic 1. So the 3.3 volts it's getting might or might not be sufficiently high to be registered as a 1. Assuming that it's sufficiently high, so far everything is fine, but it might just not work. Second, if you're transmitting a logic 1 from the 5 volt system here back to the 3.3 volt system, the transmit line that is used to transmit this logic 1 is going to sit at 5 volts. So you're essentially applying 5 volts to the 3.3 volt system, and if the 3.3 volt system is not 5 volts tolerant, it's going to break. So ideally, you should put something in between here that sort of boosts the 3.3 volts here to 5 volts when you're transmitting from over here, and reduces the 5 volts from this system back to 3.3 volts. That's what the level shifter does, and if you want to get this, one of the easiest things you could do is you could just buy a chip that does it for you. For example, this one here is quite popular. This is the Texas Instruments TXS0102. And it's fairly easy to use. You just hook up the reference voltages and you hook up your transmit and receive lines, and you're basically good to go. This chip here is a bidirectional one, which means that not only can you transmit in one direction, but it sort of automatically figures out in which direction the transmission is going, which makes it good for things like I2C. So this is something you can do. Note here that on the datasheet, this is interesting, it says the maximum data rate is 24 megabits per second for a push and pull configuration, but only 2 megabits for an open drain configuration. And we'll come back to that because this is fairly important. Instead of using one of these integrated circuits that I just showed, you can also build your level shifter using discrete components. Now you might ask why you should bother about that if there is these nice little integrated circuits that do everything for you. And apart from being aware that the discrete solutions exist and as a consequence being able to use them when it makes sense, I noticed that especially on the Arduino wiki, a lot of these circuits are kind of presented. They show you how you should wire things up, but they don't really explain how it works. And more importantly, they don't tell you under what circumstances it works. If you compare this to the datasheet we discussed before here, it tells you exactly, 24 megabits per second, 2 megabits per second, and this is important. On a related note, there is a discontinued product from Sparkfun Electronics that is a single transistor voltage level shifter. And it's the same thing. They do not tell you at what frequencies this works, with what voltages this works, and that's a bit of a problem. In fact, I witnessed somebody trying to use this very level shifter for an application where the frequency was just way too high and a lot of time was wasted. So I think this product from Sparkfun is not that great but not because of the circuit, but rather because the way it is presented. If you think about it, either you know how this level shifting business works. So in that case, you know that you can use a single transistor, you know that there is some drawbacks involved with that, and you might be able to figure out whether you should do that or not. And if you decide to do it, you just buy your transistor and design it into your product. On the other hand, if you don't know anything about level shifters and you don't want to bother about it, then you might feel tempted to just buy this level shifter from Sparkfun and it just might not work. And I think that there should be some sort of data sheet telling you under what circumstances this stuff works, and they just don't do that. So in my opinion, that's not that great. So anyway, this is the schematic of this Sparkfun product here. I link in everything in down below, even though the product has been discontinued. As you can see, there is two channels, channel 1 and channel 2, that are exactly the same. So I'm just going to discuss one of the two channels. You can see that there is a voltage divider here. In case you can't read it, that's a 20k resistor and that's a 10k resistor. And if you apply 5 volts up here, the voltage is just going to be divided by this divider here, and you'll end up with something that is reasonably close to 3.3 volts at the center point of the divider. There is two minor issues with that you should be aware of. First off, if you, for whatever reason, apply a voltage that is higher than 5 volts, of course the voltage at the center point is going to be shifted accordingly. So you just have to be aware of that in case you hook up a sensitive part or something. There is no input protection or voltage protection whatsoever in this circuit, which you really couldn't expect from just two resistors. Second, if the part that you're hooking up to the center point of the divider has rather low impedance, it's going to parallel up with this low resistor here. So essentially the resistance of the lower part of the divider is then going to be lower than 20k, and as a consequence your output voltage is going to be lower than 3.3 volts. So this is just something you should be aware of. To step up the voltage from 3.3 volts to 5 volts, this transistor circuit is used here. And I redrew this circuit on a sheet of paper to be able to discuss it in a little bit more detail. As you could see in the schematic before, the transistor used in this circuit is a MOSFET. So just in case you're not familiar with how MOSFETs work, let's briefly discuss that. What I'm explaining now holds true for an N-channel MOSFET. You have three terminals, the drain, the gate and the source, and you're essentially looking at the voltage difference between the gate and the source. If the voltage difference between the gate and the source is less than a threshold, the transistor is off, which means that there is no connection between the drain and the source. If, on the other hand, the voltage difference between the gate and the source is larger than some threshold, the transistor turns on, which means that you have typically a low resistance connection between the drain and the source. That could be if the transistor is fully turned on, 1 ohm, 2 ohms, maybe 0.5, 0.1 ohms. It really depends on the transistor. So let's make an example. If the gate is sitting at 3 volts and the source is also sitting at 3 volts, VGS, the difference between the gate and the source voltage, is 0 volts because both terminals are sitting at the same voltage. Hence, 0 volts, clearly for sure whatever threshold we have is lower than this threshold, so the transistor is off. If your gate sits at 5 volts and your source sits at 0 volts, VGS is 5 volts. And if, let's say, your threshold is 2 volts, then VGS is above the threshold voltage and the transistor is on. For P-channel MOSFETs, it's just the other way around. So to turn on a P-channel MOSFET, you have to pull the gate of the MOSFET below the source, and then it's going to turn on if you exceed the threshold voltage. It's also important to note that what I just explained is a model. It's called the threshold model of MOSFET. This model is able to reflect a few aspects of the transistor, but it doesn't reflect many other aspects. For example, things like the linear region is not reflected at all. And it's always important to keep in mind that you have to pick the proper model when you're making any considerations. And this is the actual circuit. There is a 5 volt reference here, a 3.3 volt reference. These references are always on, which means that they do not depend on the actual input and output signal. It's just always 5 volts and always 3.3 volts. You can see a pull-up resistor here. The 3.3 volts is always connected to the gate, which means that the gate always sits at 3.3 volts. And then you apply your input signal here, which is transitioning between 0 and 3.3 volts. And what you get out is an output signal that you can get from the drain of the MOSFET here that is transitioning between 0 and 5 volts in harmony with your input signal. If your input signal sits at 3.3 volts, then the source is at 3.3 volts because this is directly connected to the source. The gate is always at 3.3 volts because it's directly connected to the reference, which means that your gate and your source are sitting at the same voltage and the transistor is off. So essentially you could just imagine that the transistor wouldn't be here at all. And in that case we have this 5 volt reference here, a pull-up resistor, and this point is just sitting at 5 volts. So if the input is at 3.3 volts, the output is at 5 volts. This is assuming a high impedance at the output. If your input signal is at 0 volts, the source is at 0 volts. The gate is still at 3.3 volts because it's connected directly to the reference, so there is a 3.3 volt drop between the gate and the source. And this is sufficient to turn the transistor on, which means that there is this 1 ohm or whatever it is, probably even lower than 1 ohm, connection between the drain and the source, and this drain point here is then pulled to a very low voltage, like 0 volts or something like that. And as a consequence, your output is sitting at 0 volts. So if the input is at 3.3 volts, the output is at 5 volts. If the input is at 0 volts, the output is also at 0 volts. And that's exactly what we want. So I breadboarded the circuit and I'm going to apply an input signal. In my case, it's just a square wave between 0 and 3.3 volts. And we're going to look at the output signal and discuss under what conditions this works. Okay, so I built up the circuit. I have the function generator running at 1 kHz right now. The top trace is the input trace from the function generator, 3.3 volts peak to peak, and the bottom trace in blue is the output waveform, that's 5 volts peak to peak, and so far this doesn't look too bad. But if you look closely, and I'm not sure if you can see that on camera, but if I turn on the cursors, it's maybe becoming a bit more apparent. Both the input and the output waveform, actually, when they're supposed to be at 0 volts, they're not. There is something like a 200 to 250 millivolts offset that we have to investigate because that's a little bit weird. Furthermore, if I increase the frequency from 1 kilohertz to say 1 megahertz, and I correct the time base for that, you can see that we have a really crappy output waveform. Instead of a nice and fast rising edge here, we get this kind of almost just like an RC charging curve. We're going to talk about that. And it's important to address this somehow because if your receiver depends on this actually to be a nice square wave, maybe it's measuring the pulse width of the high pulse or something like that, then there is no way this is going to work. So let's get back to our piece of paper and try to figure out what is going on here. To summarize the results from this experiment, there is really 2 things we learned. First, apparently while this circuit works fine at lower frequencies, the output signal starts to degrade when you step up the frequency. Second, for some weird reason, the output voltage is actually about 250 millivolts above ground, when it should be 0 volts. And the reason for this second issue is that I'm using a function generator to generate my input signal. And this function generator has a source impedance of 50 ohms, which means that inside of this path here, there is actually a 50 ohms resistor. And when you ground the input here, you will have a voltage divider between this resistor here and this 50 ohms resistor inside the function generator. And if you do the math, you will see that the voltage divider that is built from this resistor here and the 50 ohms source impedance actually will lead to pretty close to these 250 millivolts offset that we saw. You might now argue that usually you're not using a function generator to generate this waveform here. But still, what this really means is that whatever current you have flowing through the resistor, through the MOSFET, is then going to sink into your transmitting device. So you have to make sure that your transmitter is able to sink this current. Addressing the other and arguably larger issue of a completely distorted output waveform, you have to realize that every component has parasitics. In the case of a MOSFET, among other things, this is stray capacitance between the drain and the gate, between the gate and the source, and also between the drain and the source. So if you actually know how a MOSFET is physically built, it makes perfectly sense. I tried to sketch this over here, that you have this stray capacitance. But what this really means is that when you want to output a logic high at 5 volts, you first have to charge the capacitor between the drain and the source. This capacitance here it really depends on the MOSFET, 10, 20, maybe 30 picofarads or something like that. And actually the breadboard I'm using is adding at least the same amount of capacitance to this stray capacitor there. So you have to charge this capacitor. If you do the math, you will see that this takes more than 100 nanoseconds to do so. So there is this inherent problem of first charging the capacitor before you can actually get your desired output voltage. How could we fix that? One way would be to reduce the resistor up there, because if this resistor is smaller, then this stray capacitor is going to charge up faster and you're not going to have that long ramp up in there. But if you reduce this resistor here, there is more current flowing through the MOSFET and into your transmitter. And as I said before, your transmitter is not supposed to sink that much current, so that's really not the way to go. Especially if you actually do the calculations, you'll see that you have to reduce this resistor by several orders of magnitude to get the desired result. And that's just going to lead to a current that is far too high. There is another way to address this problem. In order to understand this, let's have a look at the following circuit. This is a classical CMOS inverter. It consists of two complementary MOSFETs, an N-channel MOSFET down here and a P-channel MOSFET up here. What this circuit does is, whenever the input is low, it's going to output high. Whenever the input is high, it's going to output low. The characteristics of this circuit is that this is a push-pull stage, and we're going to understand why it's called like that. But it's important to note that there is no resistor as there was in the other circuit that we have. This other circuit here, let me put that on real quick. The other circuit had this drain resistor here, and in fact this output stage is called open drain because you have to connect a pull-up to a drain that is otherwise open. On the other hand, the push-pull configuration doesn't have that. And we're going to discuss this in a little bit more detail. Let's assume for all examples that the threshold voltage of both transistors is 2 volts. If the input sits at 3.3 volts, this gate here is sitting at 3.3 volts also. The source is grounded, so VGS for this lower transistor is 3.3 volts. That's larger than the threshold voltage of 2 volts, hence this transistor will be on. It's a little bit more complicated for the p-channel MOSFET here because you have to invert everything. But if the gate sits at 3.3 volts and the source at 5 volts, VGS is going to be minus 1.7 volts. And that is actually not sufficiently low because it has to get below minus 2 volts for this transistor to turn on. Hence, this transistor is off, this transistor is on, and the output sits at 0 volts. Remember that this was with an input of 3.3 volts. If the input is 0 volts, however, the gate sits at 0 volts, the source sits at 0 volts anyway, so VGS is 0, this transistor is off. If the gate of the top transistor is 0 volts, VGS is minus 5 volts, and in absolute terms, that's larger than the threshold of 1.7 we need. Of the threshold of 2 volts that we need. So this transistor here is going to be on, and the output will be 5 volts. So when the input is 3.3 volts, the output is 0 volts. When the input is 0 volts, the output is 5 volts. So in theory, apart from the fact that this is inverting everything, that should do the job. And in fact, I could go out and look for transistors that match this requirement of a threshold voltage of 2 volts. However, I'm not going to do that because first of all, I can't be bothered. But second, if I mess this up, then both transistors are going to be on at the same time. And I would have a short between my supply rail and ground. And I don't want to have that. And second, and of course more importantly, if I built this out of discrete components, we never talked about any voltage that is somewhere in between 0 and 3.3 volts. And it might happen that both transistors are going to be on at the same time intermittently, hence again shorting my supply rail to ground. So I'm going to do something else instead. This is the datasheet of a CMOS buffer chip. Actually, it's the M74HCT125. And what this chip does is it senses whatever logic state it has at the input and reflects it at the output. You can see that there is this inverter stage that we just discussed built right at the output. So because this has this push-pull output stage here, it should not suffer from the problem that we encountered with the open drain circuit before, and we should be good to use that. Note also that between the input and the output, not only is there this inverter here, but between this node and this node, actually somehow the signal has to be inverted yet again. Otherwise it wouldn't be a buffer, but it would be an inverter. There is one more thing that you have to consider when you want to use this logic buffer chip as a voltage level shifter, which is in the end, when you input 3.3 volts here, you want to have 5 volts out, right? So you have to make sure that 3.3 volts is high enough a voltage that it is recognized as logic high. And you can't take this for granted. But if we look at the datasheet of this particular chip here, there is another table later on in the datasheet that tells you exactly what voltage you have to meet to recognize your input as logic high or logic low. Here there is this VIH figure that tells you that for some input to be recognized as logic high, with a supply voltage between 4.5 and 5.5 volts, you need at least 2 volts at the input to recognize the logic high level, which in our case is met because we're inputting 3.3 volts and that's considerably higher than 2 volts, so we're good to go. However, I printed out a similar table from another datasheet from a chip that has exactly the same functionality. And if you look at this table, it doesn't give you the figure for a 5 volt supply, but there is one for 4.5 volts here. And we can see that we need at least 3.15 volts at the input to recognize the input as logic high, which is really close to the 3.3 volts we're ideally having at the input. So I would say that in this case the difference between 3.15 and 3.3 is just too small for this to work reliably. And in addition to that, look at the two data sheets here. If I move the page a little bit further down here, the one that you should not use is the M74HC125. The one that you should or could use is the M74HCT125. And this relates to the logic family of chips that you can use. There is maybe a dozen or so different kinds of logic families, and if you're interested in that, there is in the book The Art of Electronics, there is a really nice introduction into that topic, which gives you a nice historical overview of how all these chip families relate to each other and when they appeared on the market and what they improved. And I believe it's either chapter 8 or chapter 9. So if you're interested in that, this is really a very nice read that you can have on that topic. So let's use this logic buffer chip to boost the 3.3 volt signal that we have to 5 volts. Look at the signal quality at the scope, and hopefully it will be much better than what we observed with the first crude circuit with the open drain output. Okay, so I breadboarded the circuit with this logic buffer chip. Now, as before, the yellow trace is the input trace, that's the 3.3 volt signal, and the blue trace is the output signal, which should hopefully be 5 volts peak to peak. If I turn on the function generator, first of all I get this really nice square wave. You can see that there is a really nice and fast rising edge here, and there is a little bit of propagation delay, but I'm not too concerned about that. So that is clearly a very nice signal to work with. Also, you can observe that now this really sits at 0 volts here, and there is no weird sort of shift as we observed with the Sparkfun solution. Now that we found a satisfactory solution for boosting my 3.3 volt input signal up to 5 volts, there is really one question to answer. If the push and pull stage is superior to the open drain, why should you bother about the open drain in the first place? In this video I showed that the push and pull stage is faster than the open drain, and I also showed that it consumes less current. So what's the open drain good for then? If you consider this configuration here, this could be, for example, an I2C data line here pulled up with a pull-up resistor up to 5 volts or any voltage with different devices connected to the data line. Then each device can pull the data line low. This is how I2C works. If this were push and pull output stages, and one device was pulling while the other one was pushing, then we would short out the rail, and you don't want to do that. So in this case, with an open drain output, any device is able to pull the line low, and if two devices decide to pull the line low while the third one is not pulling the line low, there is no problem at all. So that's just one example of how the open drain output is of use. In any case, I hope you found that interesting. If you have anything to share or any comments on that or questions, please do so in the comments, and I thank you for watching.